Yeah, okay. So we have Jason Rute following Stan with some more GPT fun, this time applied to Lean. So yeah, thank you, Jason, for coming.
Thank you. Thank you for the organizers for having me and extending my time a little bit. And thank you for Stan for giving a great intro to this talk. So I'm going to talk about LeanStep, a dataset for interactive, a dataset environment for interactive neural theorem proving. And this is, oh, sorry. Okay. This is joint work with Jesse Han, Tony Wu, Ed Ayers, and Stanislas Polu, as well as with thanks to the Neural Deformal team at Google AI. So in January of 2016, Nature published this article on the game of Go and how a relatively unknown company at the time, DeepMind, who's now owned by Google or Alphabet, solved or created a system that played the game of Go at the championship level. And this was really remarkable, not just because it was something that people didn't think would happen for a number of years, but also when you actually read the paper, like you were struck at how simple the algorithm really was compared to other previous systems. And many people have realized that even though the game of mathematics is a much harder game than any board game, and it's more of a puzzle than like a competitive game, it's still many of the ideas in that paper and other papers that have come since then can be applied to formal theorem proving, especially when your goal is not to solve the Riemann hypothesis, but just create tools for formal theorem proving and for formalization. So how would one go about doing this for a theorem prover? Well, first you need to get mathematical training data to train your model. And then you would train some kind of machine learning model like a neural network on that mathematical training data. But it's not useful enough to have a neural network unless you can incorporate that somehow with the prover and build some kind of testing environment where you can have the neural network see goals and apply them to or suggest tactics for the prover to use. And then finally, you would execute some sort of proof search using this model as a guide. And that's what we're going to talk about today. So this has actually been done before in many of the interactive theorem provers. They have created, various groups have created data sets. They've created environments where an agent, automated agent can interact with the theorem prover, and full-blown machine learned provers. One of the first was Tactic Toe for Hall 4. And then as far as provers go, Deep Hall for Hall Light, which is one of the best ones out there. It's by Google. And in the metamath realm, there's been a few, culminating in the GPTF that Stan just said, which is also one of the best provers out there. And I really appreciate Stan's focus on making it usable to metamath users. In Coq, there's a number of things. One that I like to call out is Tactician, which again has this focus on being usable to actual users of Coq. And in Mizar and just first order logic in general, there's also a lot of work in that realm, but nothing in Lean so far, in Lean 3 or Lean 4, and that's what we'd like to change. So the state of machine learning for theorem proving, there's been a lot of things that we have tried as a community in the machine learning and theorem proving world. Things like tactic selection and lemma selection using machine learned models, or as in case of GPT, just full proof step text synthesis. We've tried different neural network architectures and other machine learning algorithms and some simple reinforcement learning. And I consider that to be kind of a first step. And in that first step, the results have been very encouraging. These various systems, depending on how you count the numbers, it very much depends on your evaluation framework, can solve like 20 to 60% of the theorems in the library. And This performance is similar to that of hammers, but it's complementary because many times it solves different theorems than hammer type systems, SMT-based hammer systems would solve. As we saw with the previous talk and with others, this is starting to be incorporated into theorem provers in the same way that hammers are. And many of the AI labs, such as Google, OpenAI, Facebook, DeepMind, IBM Watson, they're interested in this because they see this as like symbolic reasoning is really kind of the next frontier in AI. And many of them are interested in Lean, which I think is really great for this community. I think there's a lot more to do. And this is very much my opinion on the things. I think other people would have different opinion on what the important things are, but I think there's been a lot of work in self-supervised learning and reinforcement learning that theorem proving can incorporate, need for better benchmarks and things unique to theorem proving, like lemma creation, definition creation. And that really is why I think theorem proving offers a very interesting space for experimenting with machine learning ideas. Program synthesis, and other people want to use archive proofs or combine with traditional like SMT solvers. And of course, many new ideas. But I think the main point I'm trying to get across is while we're just getting started, it's already very encouraging, and there's a lot more things that we know we can try, as well as things we need to think through as next steps. Okay, so if we want a data set, how do we get a data set of data from Lean to start training machine learning models? As you probably know, Lean is made up of two types of proofs. You have tactic proofs and you have term proofs. And first, let's talk about how we can get data from tactic proofs. And we're going to call this data set LeanStep, because these are proof steps in Lean. So tactic proofs, what sort of data would you like from a tactic? Well, first, if I have this tactic like cases H with HPHQ, I would at least like that string, cases H with HPHQ. I would probably also need what were the hypotheses and goals right before that string, because this is, as a user of Lean, that's what you see. You see the goals and you say, I'm going to apply this tactic to work on those goals. Be also good to have things like the tactic name and the tactic arguments. But once you start getting into that, you start getting into this fact that tactics are really this each tactic has its own grammar. And that grammar is sugarcoating for something inside Lean, which is a little more Lean-like. So it'd probably be good to have not only the tactic arguments, but also the reflected expressions that those arguments represent. Now, a tactic is, proofs are not just lists of tactics. They're nested, they're combined with various combinators. And it would be good to just get a full abstract syntax tree of every proof. It would be good to have the declaration name. And there's so much hidden information also in the tactic state, like what namespaces are open, information about the environment, possibly all the declarations, or at least things like simp lemmas, meta-variable information, and other hidden information. So very briefly, let's just talk about how we got this information. There is this piece of code in LeanForward library called iStep. It is run every time you run an interactive tactic, and only when you run interactive tactics. And so you can modify it to trace position information, namely the start position of the tactic with the line and column, as well as any information in the tactic state at that point. So you can get the goals and the hypotheses and things like that. And then if you compile mathlib with this tracing code, you can trace it and then process it into something useful. But that only gets us the start of the tactic. It doesn't get us the full tactic or the tactic arguments. To get that, what we did was we modified every tactic declaration in Lean and Matlib. And of course, you don't want to do this manually. You want to write it like a script to do this. And that's what we did. We wrote a script to find all these declarations and to modify them manually, where we slightly tweaked with the parser framework, not the C++, just the Lean, to record the start and end of every argument as well as what the reflected expression is. And we could get other things too, like the type of the expression. So that is, that's how we got the data. And then we had to combine it too as well, which was also a lot of work. Now, what the first data set, we actually have a lot of data here, but the first data set is going to be fairly simple. It's just going to be what are the pretty printed hypotheses and goals, the exact thing that the user would see if they're working in Lean, and what is the human written tactic command that lives in the code base. And so we got that data set, and the idea would be that we could train some model. Just here are the hypotheses and goals, output a tactic command in just text as a string. And that would be good for transformer models like the GPTF model that we just saw. So this is the LeanStep tactic proof data set. It's going to consist of 138,000 tactic goal pair or goal tactic pairs. That is about 19,000 theorems with containing tactic proofs. Now there's actually about 42,000 theorems. Of course, many of them not containing tactic proofs. But 19,000 theorems is pretty good. And of course, you as a MATLAB user can increase this data set by just adding to MATLAB. And since MATLAB, basically doubled in the last year, there's a lot of room for this data set to grow. What are the most common tactics? You can see here, rewrite, simp, exact, apply, have, cases, and so on. Okay, some quick highlights of this data set. All the tracing code was written in Lean.
Sorry, Jason.
Yeah.
Quickly ask a question about the previous slide.
Yeah,
sure.
Sure.
So you generate this data set using this modified version of Lean and MATLAB, etc. And you used a Python script to modify it, but you still had to do some stuff manually. Does this mean that like 6 months from now, when MATLAB is a lot bigger, it will be a lot of work to generate a new data set? Or
no.
Is it
no,
basically push button?
Yeah, so that's what I'm trying to convey on this slide. That what we're actually doing is automatically injecting this tracing code into Lean with some Python scripts. So like I can just, in the Lean package .2ml file, just change the version of Mathlib, run my script, and it'll run our script, and it'll just do it for that version of Mathlib. So it's very nice in that way, in that we can change the version of Lean, we can change the version of Mathlib, and there's no real issues as long as someone didn't like totally mess with the parser framework.
Okay, that's really cool.
Also, because the tactic recording tracing code is Lean, we can get whatever we want from the tactic state as long as it's available to the Lean monad. So if you want information about declarations in environments or meta variables, that's all available by just making modifications to how the information we trace. Also, the thing I've learned about machine learning researchers is none of them want this data in the same format. We right now have been working with pretty printed strings, but others would want maybe strings with more information like the PPL strings or raw format or S expressions or JSON or some kind of simple to compute vector embeddings. All of that's possible as long as you can write it in the Lean tactic framework. And that, I think, makes it very extensible for a lot of different research purposes. And as far as I can tell, it seems to work flawlessly. Like we can capture every interactive tactic application without issue, which is something we wouldn't be able to do if we tried to use like the Lean server. And the data set and code will be made public hopefully soon, but we'll wait till it's ready to go. Okay, and I think this data set also has some other uses besides machine learning, although the intent was certainly for machine learning. In the process of making this, we discovered that there's a number of tactics which are never executed. They could be removed from the library. If you want to know basic statistics about Mathlib, like what are the most common tactics, I showed that on a previous slide. What is the longest tactic proof, etc. And I think for porting to LeanForward, this might be useful because now we have like a full abstract syntax tree where we've broken up all the tactics by their combinators and how they all combine for every tactic proof. And that could be some ways to automate that into LeanForward code, but we'll have to see. So that was tactic proofs. Let's talk about term proofs. Lean stores term proofs for all theorems. So even if a theorem was proved in tactic mode, the proof that's stored in Lean is a term proof. And it's easy to get this proof. You just do print and the name of the declaration. And also with using the metaprogramming framework, you can loop over all declarations and find their proofs. So given that we have access to all the term proofs, what can we do with that information? And one thing we can do is the following. So I think we all know, if you've used Lean enough, that if you have a term proof and you have a hole in it, there's some part you don't know how to fill in, you put an underscore as a hole, that creates a hypothesis and goal that you can then fill in with a term. Now, if we have the full proof, we can just take any sub-expression or most sub-expressions and replace them with holes. And then we get hypotheses and goals, as well as we know what fills the holes because that's what we removed. And that gives a very useful data set for a number of purposes. A few tasks you can do with this data set are, the first task is probably the most obvious, is if you have a partial proof term with a hole, you can say what fills that hole. And we have a data set. And that's very similar to a data set that Google worked with earlier this year called the skip tree task. Also, since we have hypotheses and goals, we can say, well, what proof term fulfills that hypothesis and goal? And we have that. And that's very similar to tactic proofs. If you just put an exact or an apply in front of that, you'd have a tactic proof. Also, there's other tasks we could do. So for example, we can ask, is that a hypothesis used in the proof of the goal? So if you look at these two examples here, true if and only if A, that probably uses the hypothesis A only if true, if and only if true. Whereas, or I mean, it would have to use the hypothesis. There's no way around that. Whereas the second one, there's lots of ways to prove true without having to use that hypothesis. So it probably doesn't need it. And this is a data set that we could also train a model on. And finally, we could train, rather than on the full tactic proof, the if and only if .sim h, we could just say, what is the main function, the outermost function in this proof? And we could train on that. And either train on the function name or its type, which is something that, you don't have to have that much knowledge of the library to know what type you need there. And okay, so why would we want some of these auxiliary tasks? Like the first two tasks are maybe obvious because like that is theorem proving. But why would we care about auxiliary tasks like that? And there's a number of reasons. One is that it provides simpler tasks that you might want to train a new method on. Like there's still kind of this question of like, how much can neural networks just as their own as like text prediction algorithms? How much can they do reasoning, like just symbolic reasoning or something that appears to be symbolic reasoning? So it might be better to use one of those like later tasks. Also, there's this strong principle that I think Stan pointed to in his talk as well, that there's we all know, or a lot of us know, that neural networks are very data hungry. But there's lots of ways to augment your data set to create more data. And so we talked about how, we could turn some of these term proofs into tactic proofs by putting just an exact in front of that proof. And that would increase the tactic proof data. We could also possibly train a model on one of these other tasks, and that model would learn something about the input, because these last three tasks have all the same input as the tactic prediction task, but they have different outputs, and that's fine because you're still learning something about the input that could be possibly useful to the model. And as well, it's possible that some of these tasks would just be useful in general as tasks in theorem proving, as like subtasks. So that's another possibility. So those were the data sets. And now let's talk about the environment. Because again, you're not going to be able to do much unless you have some environment that to interact with a model. So we're going to train a model, which we'll talk about at the end. But once we have that model, we need a way for it to interact with Lean. We want it to take in the hypotheses and goals as pretty printed strings and output a tactic that we can then apply into Lean, and then Lean will give us a new goal to explore. And if we have that, then it's possible to do various tree searches or searches. So we're going to do just a simple greedy search similar to the tidy tactic to test this out on. So here's a reminder of how the tidy tactic works. In tidy, there is a fixed list of tactics, and it applies them in sequence until one works. So it'll first try REFL, and then exact decidable trivial, and then assumption, and then intros. And then once one of them works, it never looks back. It applies that tactic, and then it repeats the process again until it gets to solving all the goals, or until it until it reaches a dead end or a limited number of steps. And we're going to do the same thing, but instead of having a predetermined list of tactics, we're going to query our model for a number of tactics, maybe 10 or 64, depending on how many we want to choose from. And just to be clear about a few things here, even though that these neural networks are in some sense deterministic, what they really do is represent probability distributions that you can query from. And that's what we're doing. We're querying these probability distributions. Right now we're querying them at random. So there's no ranking of these. The first one that we get isn't any better than the second one. We're just going to go through them in order and find whichever one works. And again, this is just, these are just going to be text models that just are going to dream up tactics. They might be gibberish, or they might be great, or they might make up tactic names or theorem names, or they might be like exactly what we need for that situation. And then we'll apply it if it works, and never look back and follow this greedy search until we've reached our fixed step or dead end or solved the goal. Okay, so, one more thing I want to mention about this is that obviously this is a simple tree search, and a better tree search would be better. Like if there was any sort of backtracking, breadth first search, depth first search, Monte Carlo tree search, beam search, so there's many options in improving this. And this is just the first thing we wanted to try. So the preliminary results, and I should really emphasize the word preliminary here. Many of these are within the last week. Some of these are in the last 12 hours. So, so keep this with a grain of salt that we can definitely improve these results in some obvious ways. We're going to train a model. We're going to train a model on 80% of our LeanStep tactic proof data. And we're going to train it on this task where here's the hypotheses and goals. What is the tactic to apply? It's going to be a text prediction model similar to like what you saw in GPTF. And we're going to test this by finding theorems that where none of the proof steps in those theorems were used in the training data. So they're completely disjoint from the training data. And then, so we have about 3,000 of those. And we're going to test them just using our greedy search procedure that was similar to the tidy tactic, but using our model for guidance. And we're also going to compare against tidy tactic as a baseline because it uses a similar sort of search. So there is a public library called FairSeq, which allows you to train transformer models. And we're going to train a model of about 50 million parameters, which is big, but it's not too big. It's something that academics can train on. And it's going to create 10 candidates that we can choose from for that step. The results are as follows. So the first result is just how well does it do at predicting the tactics in the test data, the data that wasn't used for training. And so about 14% of the time, it just picks the exact same tactic that the human said in that situation that's in MathLib right now.
Can I clarify? Is it predicting the parameters too? So if you give a chain of like 5 rewrite steps. Every rewrite step is exactly.
Every rewrite step exactly in the same order. All the variables in the, the exact same variables. So it's really not that useful of a metric because obviously there's lots of equivalent tactics you could use at any point in Lean.
And even the naming in the cases H with HP, HQ, the HP and HQ must be the same.
Yep, exactly. So it's very, So it's really not the most useful metric, but it's just kind of a first pass. The more useful metric, I think, is how well does it do at proving theorems. And in our case, using this greedy search strategy, it proves about a little less than 12% of the theorems we gave it as test theorems, compared to tidy, which proves 11%. Now, the proofs are a little shorter, probably because it has more tactics available to it, because it can just make up whatever tactic it needs in that situation. Also, it's fairly complementary with tidy. When you combine this fair-seek model and tidy, then you get up to 17% of theorems. And you can see here a bar graph of just how much we prove. The fair-seek models in blue and the tidy models in red. And so for some libraries like control, we do much better than tidy. Analysis too. So.
Oh, but you even beat it in category theory. Tidy was basically developed to help with category theory. So that's funny.
Yeah. Now, of course, this model can also pick any of the tactics that tidy would have picked. So it is certainly possible for it to do better.
Can it pick tidy?
What'd you say?
Can it pick tidy itself as the tactic?
Is there any tidies in the library?
Probably not very many explicit ones, yeah.
Okay, then it probably won't do it very often because it tries to follow what humans do. Okay, so we thought that was good, but we're like, well, what if we go bigger? What if we work with OpenAI to train a model similar to the GPTF transformer? And so we did that. It's 3 billion parameters, which is pretty big. It will generate 64 candidates. And now it predicts the exact same tactic as in our test data 20% of the time, and it proves almost a quarter of the theorems. The proofs are somewhere between fair-seek and tidy in length. Also, this model is kind of by its nature stochastic, random. So, or not random, but samples from a distribution. So it'll get a different result every time. And if we just try that greedy strategy 8 times in a row, it'll try different tactics every time. And then if we combine those, then we can get up to almost 36% of the theorems solved, which really, I think, shows that if we just implemented better tree search, we could do much better because, let's just try again with a different tactic that it predicts rather than just taking the first one that works. And then here again is a breakdown. Again, you pointed out like category theory, is much better now. Logic does way better. Tactic improves half of the theorems in there. So I think this is pretty encouraging results. We decided, wait, what happens if we even scale it up more? So we tried a 12 billion parameter model. And in that case, GPT proved about 25 or almost 26% of the theorems. And the proofs were a little longer, which might indicate that it's able to kind of learn, think further down the line in a sense to learn longer proofs. And again, you can see the results here. There's also, because of the stochasticity, I think there's a lot of possibilities that that once we implement better tree searches, that these results will also stabilize more, because there's a lot of places where the 3 billion parameter model does better than the 12 billion parameter model. And it's not clear how much of that is due to just randomness of what we get from the model. And then here's a summary of the results. Again, yeah.
Is this, in the test sample, does it only have theorems that were proved using tactics, or is this term mode and tactics?
Well, yeah, the test is theorems that only use tactics right now. We've looked a little bit at other theorems, but also in some sense, the kind of the point of this is showing that a model can do tactic reasoning. So the sort of theorems that you do term reasoning on, it wasn't really, trained on that sort of data. Whereas we certainly have that sort of data, we could train models on that sort of thing.
Mm-hmm.
But that's a good question. It was theorems that have tactic proofs, or at least tactics are somewhat involved in the proofs. So here's the summary, and again, when we train more than one model, or when we try the model like 8 times in a row, the large model, it does better than just if we go up. So I think a better tree search or better search procedure would really help here. But the larger model that is showing that it really has some good potential too. So I've often said that I don't think that these numbers are as useful unless you can actually put this in the hands of someone who uses this sort of thing on a day-to-day basis, and it can tell you, is this actually a useful tool? Is this learning, something about proofs? And that's what we did, because Lean has a wonderful meta-programming framework, which allows you to do a lot of cool things. So we made a tactic which queries this model through an API, and then outputs the various predictions that this model gives and which one, and what the first one is that works. Now, we call this interactive neural theorem proving, with the idea being that we have a neural theorem prover, like this greedy search, guided by a neural network, but you can put a human into the loop. You can say at any point in this, the human can say, oh no, I actually want this tactic, or let's just go with this other thing, and then keep applying this. You could also think of this as neural interactive theorem proving, where we have neural guidance to the human doing interactive theorem proving in many ways, in the same ways that you have current guidance using the other tactics in Lean, which are intended to give to suggestions and guidance to the user. And I'm going to turn it over to Jesse now, who's going to give a live demo of this.
Thank you, Jason. I hope you guys can hear me.
Yeah.
Allow me to start sharing my screen. Okay, you guys should see Emacs. Is that correct?
Looks good.
Great. Okay, so.
Oh, it's not correct. You should show VS Code.
It does work in VS Code too.
Yes. But actually, I think Emacs is the correct editor. So what you're looking at here is the GPT front end to the greedy proof search that Jason just talked about. What it does is that it just runs a single round of the proof search, namely the inner loop, where it
would you be able to make your font a couple of sizes bigger?
Yes.
Thanks.
So it merely runs one round of the inner loop of the proof search, and it has the greedy proof search at its core. And there are a number of numbers you can set here, like the number of parallel queries. This will determine the size of the list it loops over as it's trying them in a greedy fashion. The depth, namely the number of rounds of proof search you run. The temperature, which controls the randomness of the outputs, and whether or not you want it to say what tactic to try using next. So, okay, so let's try doing a hello world. So if it's so smart it can prove a third of the theorems in the test set, it should be able to prove something by raffle, right? So now the only thing we have to do is type GPT, and it says, try this ruffle. Okay, so we're off. So now let's see if it can do some more complicated logical reasoning. So I mean, this problem in particular isn't that complicated, but it's a bit harder than ruffle. And so, okay, so you can see from the predictions it's listing here that, so it wants to try intros, So it just takes the first one that works, but you can see that there are a bunch of other things that we can try here. So in fact, why don't we try intros H1, H2? Okay, let's try this again. Oh, and it manages to solve it by saying exact H2, H1.
Wait, so
and there we go.
Those are all separated? There's several suggestions in that list? Or
right, so it only runs one round of the greedy proof search, so it'll return the first one that works. But there are a bunch of other things that return because it's making 35 queries in parallel. And so you can inspect them, and there might be useful hints in there, as we'll see later.
And to answer Mario's question, I think that list is not a proof. That list is a list of suggestions.
Yeah, so it's just the next tactic that you could try applying.
Can you add a new line to one of those format.intercalate, or will that break everything? Maybe make it easier to read.
Oh, that's a good point. Let's try that again. That's much better. Thank you. Okay, and it said the same thing, so I guess it's fairly confident in this one. Okay, now let's try an even harder one. So as you can see, the workflow is extremely smooth. It returns in like a fraction of a second, and it says the right thing too. And in fact, here I think it says the correct proof term, just it's not the first one it returns. So here we could say left and then try querying it again. Or we can just try calling it once. Oops. My bad. So I'm using a keyboard macro to do the copy and pasting. Or we can just take a look at the predictions and just copy and paste the correct thing, because we know that this works. So as you can see, it's already, so it knows some basic logic, it seems. So I mean, I doubt that it's seen this goal in its test set, or sorry, its training set, because there's no reason a goal like this should appear as a theorem in MATLAB. So it's a promising sign.
So Jesse,
yes?
do you test the suggestions, whether they actually parse correctly and or fail or not?
Yeah, so I mean, what's happening in the greedy proof search is that we hacked into Lean to expose some of the internals of the parser, and it reparses it, viewing it as an interactive tactic. And then we execute it, and then we only return the first one that works.
Okay, but so
does that answer your question?
So you had like 4 suggestions, and why were there 4 in that list? Because you run 35 parallel queries.
Yes, but
31
there are some
failed,
duplicates, so we deduplicate them.
Right. Okay, makes sense. Of course. Yep.
Great. So okay, let's try to finish all of these. So okay, it wants to try intro H. Let's do that. And so if we just keep calling it, oh, it says sint H. So it'll introduce a name, and it'll see the tactic state, and it'll use the name that's in the tactic state for further tactics. And that's pretty cool. Okay, so I think this one is the most complicated looking one. It's not that bad, but yes?
Question. So why isn't it suggesting high-level automation for these propositional logics?
Probably because it's never seen these kinds of things solved in MATLAB.
Yeah, I see. Okay, yeah, makes sense.
And if they are solved in MATLAB, they'll have the term proof.
Right. Yeah, and pure term mode proofs are not included in our training data at all because they aren't captured by the interactive tactic parser. Okay, so let's try this one. Okay, it wants to try intros H1, H2. Okay, it's even being sophisticated in using the subscripts. Okay, intro H. Okay, so it didn't use subscript 3. Well, okay, now Now it says cases H1 with PQ. Okay, so now to finish the proof of false, it has to achieve a contradiction from R and not R, right? So let's see if it can do that. We might have to give it a hint. Oh no, it's getting stuck. Thankfully, we can just requery.
A lot of those look like they wouldn't.
Don't all these
actually
predictions work? Yeah, I'm confused.
Not quite. Well, I know they don't work because Lean says they don't work, but we can see that it has the right idea, right? So it wants to apply H2 somehow. It just keeps applying the incorrect arguments to them.
Well, you said that these tactics are already filtered by Lean says that they work, but those, I mean, there are some syntactically incorrect. Or...
The top list is everything that comes up, and the bottom list is the ones that work. The bottom list is the first one that works.
Yes. So since the bottom list is empty, it means that none of these passed parsing or they didn't make progress on the tactic state. But these are the things it thinks it should try. And so you can see it's very confident that the hypothesis H2 should be used in some way. And so we can try helping it along by saying, no, you shouldn't be supplying these arguments here. You can just say apply H2. Oh, we can't apply H2. Okay, so in fact, why don't we try refine absurd? Okay. So it can handle multiple goals just fine. Okay, so it's this exact H2P. Perfect. Okay, now it's got one more to go. Yeah, it even uses the solve one brackets. It's crazy. Okay, and we're done. So as you can see, it's super interactive and the workflow is extremely smooth. It's great. Okay, so that was just the warm up. We have some more theorems to prove now. So first, let's start with some simple ones, things that don't have to do with propositional logic. It should know how to prove this, right? So I mean, it shows up in MathLib somewhere. Oh, okay, it says R intral REFL. And then it says REFL. Okay, let's try this one. So now let's see if it can do arithmetic. So we haven't really shown it any notation yet, right? So it's just seen some basic logical symbols. And as we go further down this file, we're going to go deeper into the algebraic hierarchy and see if it can say the correct things when it sees like fields and groups and so on. Okay, it says simp nat.addcom. Okay. Well, okay. So I can't think of any human who would write something like this, but apparently it thinks it's a good idea to try.
It's running in circle. It's back to the original.
Yes, but wait, so could we have just used this? Oh, we could have. Great. Okay, let's try this one. Suckadd. So if it's smart, it should just say like simp of suckadd, because note that while the prompt is precisely the tactic state that's emitted by the Lean server, so it doesn't say the name of the theorem it's proving. So it has to know how to infer the name of the theorem from the type. So let's see if it can do that. And what does it say? Oh no, it doesn't. It just says rewrite add suck, suckadd, which is an extremely verbose proof, but like, okay, it works. You know, sometimes you see these proofs and you wonder if it's trying to play a joke on you or something. Okay, interesting. So I think it's not doing anything. Wait, oh wait, no, my goal state's not updating. Okay, it's doing something here. Okay, it's reassociating. what's happening here. Okay, it's rewriting using adcom. And wait, what? Well, I mean, okay, I guess it works. So it never actually used some lemma called add write com. But instead it just like searched for rewrites and it somehow managed to bumble into the answer.
So
Super
how
cool.
hard would this be to set up for users?
Not hard.
Like
there's
we
two
all-
using it
questions
right
here.
now.
Well, there's two questions. There is if we had a model API that everyone could use, it's built. The question is about the availability of a trained model in an API.
Yeah. So perhaps Stan would be the better one to be able to answer this, but I...
Yeah, so these are served by OpenAI API. So basically the model we train, we put them in the API and Jesse is right now using the public API to interact with it. The public API is in private beta, but there's no reason why we wouldn't be able to create even an intermediary server for everybody in Lean to use that, and so that's no problem. It's just a little bit of work, and we're really keen on making that available to the community.
Yes,
but
so the command
these
is
all run over the network, though, right? So
yes.
When you're using this thing,
yeah.
you
So the
usually
command
have
is
to at least wait for it to go on
so
the
it's
network.
using io.command to run a curl request, and as
Yeah,
you
and
can see, it's almost instantaneous.
To run that at work, you would need 8 GPUs on your machine anyway, so you want it to run it over the network for sure.
Yeah. So in this case, it's not being run locally. So it would be very easy to scale it up to multiple users or thousands of users. So if you're a Lean Power user and you'd like to play with this, feel free to send us a message.
You better clean up your proofs before you submit them to MATLAB, though.
Oh, interesting. Yeah, that's true. Not really sure about this one.
Well, do you think that GPT would be able to help here with proof golf? Like
proof golf?
I mean, it seems like something that it could absolutely do, right?
Yeah, it is. It hasn't been trained for that, but you certainly could try co-training it on a golfing task where you feed it a special prompt that says you are supposed to golf your input, not predict what the next tactic application will be.
Like if you had
so in fact, there's work in progress.
A tactic that has a particular goal state before and also a particular goal state after, try to figure out a tactic that performs that, which is as short as possible. So like in this case, you did something
so you mean
like
a tactic
an
which
adcom,
has the same behavior on the tactic state, but is shorter?
Yeah.
Yeah, that is certainly something that we could create training data for and train on. So as we've said multiple times.
Even the current model, I guess, with if you pour compute at search time and you just search and starting from the goal and you stop when you find the second goal and you just do that as much as you want, you might be able to find short proof. I mean, we know for a fact that it worked with MetaMask to some extent.
We could compare all our test theorem proofs to what was actually in MATLAB, so it's shorter.
Yeah. So on average, the models are finding shorter proofs than at least tidy, say. Partially due to the fact that they can synthesize lemma names as arguments for simp, say. So it means that that proof search has to do less work than tidy. So okay, it was also able to get this one. Perhaps this proof is not that optimal either, but at least it's doing it in only 2 rewrites and not 3. And furthermore, it's like supplying all of the lemma names, which is super cool.
Jesse, by the way, we're already into the coffee break time, so this is super exciting, but maybe like the highlights of the examples would be great.
Great. So in fact, so jump down here and show you a really interesting one. So now we're proving a lemma about lists. So if we just try calling GPT on this, you can see that it tries something interesting. It tries synthesizing a lemma which is not actually in mathlib and is actually incorrect. It says append com, which like makes sense if you look at the syntax of this, right? Like there's some kind of append and the arguments are being reversed, and so you want append com. And for some reason, it's like really, really eager about this lemma. And so here's where you have to like start interacting with it. And you can try guiding it towards a better place. And so, well, if you're in a list proof like this, the first thing you should try is induction, right? And now the goal state looks more reasonable. So now you can try querying GPT again. What does it say? Okay, so it knows that that's REFL. And let's see if it can get the induction hypothesis. Well, okay, it's just a reasonable looking simp. Split. Okay, it should get this one. It knows how to do REFL. And REFL. Well, what was this goal here? Okay, yeah, that's obvious. Okay, so yeah, I guess I'll skip the rest of these examples because they have a similar flavor to the other ones, and I'm going to hand it back to Jason now. Let me stop sharing my screen.
By handing it back to me, I think he means just to want to thank everyone for attending the talk.
Yeah, thank you too. That was, yeah, it's fun to see this, especially the demo actually happening. So we have time for like one or two quick questions, I think.
Questions?
Yeah, I don't
question to.
Yeah.
No, question to Jason. Yeah, Jason. So is currently the environment capable of serving as an interactive environment for reinforcement learning?
It is, many of the ingredients are there. If you're willing to write the reinforcement learning in Lean, yes. If you went on something available.
Well, so we do have a REPL, so it could be instrumented.
Yeah, I mean, we're very close to it. It's just a few more details need to be worked out. But it's, you know, Lean has a great great I/O framework, so it shouldn't be that hard to instrument things.
Yeah,
I just don't want to make any promises right now because we still need to work out some details.
Yeah, thanks.
Two very quick related questions. So in your data set, do you see the intermediate states when you have rewrite with several rewriting on one line? And when you give rewrite a list of lemmas to use? And the related question is, can you specialize what the GPT tactic is trying to do by telling it that you only want rewrite as output to get a kind of rewrite search backed by a GPT?
As far as the last question, not within the current one. I mean, theoretically in these models, you can, especially if it's the beginning of the model, you can say.
Like you can just include an extra prompt that says synthesize rewrite.
So probably rewrite it'll autocomplete with the arguments.
Yeah, you basically, you give it an initial segment and then it fills in the rest. I don't know the answer to your second question. Does anyone else have a good answer to the second or to the first question?
The first one was about whether we see the goal state in between rewrite arguments, and I believe the answer is no.
Okay, yeah.
No, that's work in progress.
I think that would, my estimate is that would give you like big improvements when you're using rewrite because you can like avoid all of those loops that we were saying.
Yeah.
Many of those loops.
Yeah, currently it's trying to do those in one shot. And we have noticed that you often can recover good rewrites just by like walking through the hypotheses it tries to rewrite with and stopping. So yeah, I agree.
And it should be possible to, there's a few different ways where we could break up the rewrites for the training data. So that's very possible and doable. Because once it's trained on individual rewrites, then it would know to do individual rewrites and stop after doing one.
If you try GPT in a more advanced Lean file, like you just drop it in the middle of analysis or some gnarly category theory file, does it do anything interesting or useful, or does it only, I mean, you focused on simple logic problems. Does it do anything in more complex settings?
Well, so there are complex theorems in the testing set. It's just that we chose simple ones for the purpose of our demonstration, but we do have a random sample of theorems from category theory, analysis, group theory, linear algebra that are scattered throughout the evaluation set. And their GPT does much better than tidy.
I think, Jeremy, are you asking like, do we notice any cool patterns, like things that it picks up on?
Well, even so, I guess you're saying that is used. So if instead of the demo, you were just to drop into the middle of the analysis library, you would also get kind of suggestions that looked useful and helpful.
Yeah. I mean, from the results, it seems that way. We haven't had a chance to actually look at the proofs too much. So, but if we do find some interesting stuff, maybe we can post it.
Yeah, cool.
Just as context, the GPT tactic, I think, was finalized 36 hours ago. So we just really started playing with it. That's the reason why we don't have yet a definitive answer. But I'm pretty sure it's going to be cool.
Okay, I hate to cut off questions, but we're now halfway into the coffee break. So I think now is a good time to take a break, and people should track you down on Gather, which I've just put a link to in the chat if they have more questions. So let's thank our speakers again. Round of applause. And we'll return in slightly over 15 minutes, say 18 minutes.